Hello guys and welcome back to another video, and today I'm going to be explaining all the key concepts and topics of molecular geometry, including bond angles, VSEPR theories, and all the other topics listed on the screen along with their timestamps. Now I will be assuming that you are already familiar with Lewis structure diagrams, so if you aren't, I highly suggest you watch another video and then come back to this one. Everything will just make a lot more sense that way, trust me. Alright, so let's talk about the difference between electron pair geometry and molecular geometry, as I would say a good amount of people, including myself at first, confuse the two. Electron pair geometry represents the geometric structure of an atom's electron domains, which include lone pairs and bonded atoms, while molecular geometry only represents the geometric structure of atoms bonded to the center atom. So when your teacher asks you what the geometry of a molecule is, they are almost always referring to the molecular geometry. VSEPR theory. What is VSEPR theory? Now, well, I prefer to call it VSEPR theory because I think it more accurately represents the acronym. It stands for VSEPR, valence shell electron pair repulsion. And the theory explains that electron domains will arrange themselves as far apart as atomly possible, as electron domains can also be considered negative regions around a center atom that want to be as far apart as possible. And this is all because like charges repel. And the greater the charge, the stronger the repulsion. And the distance between these electron domains is what we call a bond angle. So as I said before, bond angles are the farthest possible distance between electron domains depending on their charge. But that's not entirely true. Bond angles are between atoms covalently bonded to the center atom, not between lone pairs. So with all this in mind, let's see if you can find the bond angle in the following compounds. If I have center atom X and two electron domains, which happen to be atoms, what do you think is the bond angle between the two electron domains? Well, let's think about it. We know the electron domains will want to be as far apart as possible, which means that they will be on opposite sides of the center atom. We also know that the center atom can be represented by a sphere, and the angle between the farthest left and right positions of a sphere is 180 degrees. So bam! Simple as that. Just divide 360 by the number of atoms bonded to the center atom, and then you'll just get the bond angle, right? Well, that's actually where you'd be wrong. Because while this would be true if the center atom was a circle, it's actually a three-dimensional sphere. So our previous method of solving for bond angles becomes useless once you enter the third dimension, which happens when a center atom has 4 or more electron domains. And the math for that is really complicated and way above our pay grade, so you'll just have to memorize the angles once we get to three-dimensional diagrams later in the video. So with all that in mind, what if we had 3 atom electron domains around our center atom X rather than 2? How do you think our bond angles would compare? Oh, okay, all right, you're right. I'm sorry. You're right. It would just be 120 degrees between each particle because the structure is still two-dimensional, which means you can just divide 360 by 3. You're right. That was easy. But what if we replaced one of the atoms with a lone pair? Sorry. How do you think our bond angle would be affected by this change? Or do you even think our bond angle would be affected by this change?
Hey you, yes you watching. Pause the video and figure it out.
Well, let's see. A lone pair has a higher electron density than a regular atom, meaning the lone pair electron domain has a greater negative charge than an atom electron domain, which means the lone pair electron domain will have a greater repulsive force, pushing the atom electron domains closer together. Adding a lone pair affects both the bond angle and the geometric structure of the center atom. While the change in the bond angle can vary from structure to structure, the rule of thumb is the bond angle between the bonded atoms will always be less than before. So before we start learning the names of each molecular geometric structure, what would you say if I asked you to explain what a center atom of a molecule is? What would your response be? Well, let's be honest. It'd probably be something like, it's the atom at the center of a molecule, duh. Oh yeah? Well, what about that one? What about this one? this one straight to the molecule on the screen right now. Yeah, what would the center atom of that be? And I think you get my point, and I think you can see why that definition is far from being right. Because by that logic, what would the center atom of these molecules even be? So the way I like to think about it is the center atom is the atom with the most atom electron domains, which means that there can be, and usually will be, more than one center atom of a given molecule. So with that piece of information, with that little piece of the puzzle, I think you would be able to easily identify what the center atom of the molecules I showed you previously were.
Presenting Alexander Javier Harman.
Ladies and gentlemen, the moment you've all been waiting for. We can finally dive into learning the different types of molecular geometric structures. I know. Everyone settle down, get your learning helmets on, and get ready for some rapid fire knowledge. Yeah, no, I'm sorry. First, I will go over 6 geometric structures which are extremely common and you absolutely must know by heart. I will classify them using an electron domain ratio of bonded atoms to lone pairs. So, let's get started. 2 electron domains with a 2-to-0 ratio will result in a linear geometric structure and will have bond angles of 180 degrees. 3 electron domains with a 3-to-0 ratio will result in a trigonal planar structure, which will have bond angles of 120 degrees. Changing the ratio to 2-to-1 will result in a bent structure, which will have bond angles of around 119 degrees. 4 electron domains with a 4-to-0 ratio will result in a tetrahedral structure, which will have a 109.5 degree bond angles. 3-to-1 ratio will result in a trigonal pyramidal structure, which has 107 degree bond angles. And 2-to-2 ratio will result in yet another bent structure, but unlike before, it will have bond angles of 104.5 degrees. And as for the next set of geometric structures, you will not need to know the bond angles for any structures that are not in an n-to-0 ratio, with n being a positive number. The molecular geometric structures that are in an n-to-0 ratio are trigonal bipyramidal and octahedral structures. And I know, they may seem intimidating, but you can actually break them down into 2 separate, more familiar structures. A trigonal bipyramidal structure can be broken down into a trigonal planar and a linear structure, while an octahedral structure can be broken down into a square planar and a linear structure. And from there, I think it becomes much easier to identify the bond angles, with the trigonal bipyramidal having 120 degree and 90 degree bond angles, and an octahedral having 90 degree bond angles between all its particles. And as for the other shapes, let's quickly go over them. If an atom has 5 electron domains and a 5-to-0 ratio, it becomes a trigonal bipyramidal structure with 90 degree and 120 degree bond angles. If it is in a 4-to-1 ratio, it becomes a seesaw structure. If it is in a 3-to-2 ratio, it becomes a T-shaped structure. And in a 2-to-3 ratio, it becomes a linear structure. If an atom has 6 electron domains and a 6-to-0 ratio, it becomes an octahedral structure with 90 degree bond angles between all its particles. In a 5-to-1 ratio, it becomes a square pyramidal structure. And finally, in a 4-to-2 ratio, it becomes a square planar structure. Okay, and now that we've covered the essential topics of molecular geometry, I just want to clarify a couple things to smooth out the edges of what we've just learned. First, when drawing molecular structures, make sure that atoms are represented as singular dots, while lone pairs are represented by 2 much smaller dots. Second, use different lines for different dimensions. Trust me, it will help. Third, I'm going to quickly show you how to draw a Lewis structure diagram with correct molecular geometry. So watch carefully and pay attention. Fourth, you may come across something like this, where it shows the center atom bonded to a molecule, and it's nothing different than what you've seen. The center atom is still only bonding to a singular atom. This just gives an idea of what the entire compound might be. Fifth, the negative charge of atom electron domains has negligible difference. It's only lone pairs that have a greater negative charge, and hence a stronger repulsion force. And lastly, molecular geometry can only be applied to covalent compounds. None of that other junk. Okay guys, well, that's it. I hope you enjoyed this AP Chemistry video about molecular geometry. At the end of this video, there will be a link to another video that has practice problems of molecular geometry, probably about 5 or 6 practice problems. And yeah, I'll catch you in the next one. Peace. .90-degree bond angle and an octahedral having 90-degree bond angles between all its parts. Wow, did I really just win that? Geo, it becomes a square planar structure. Thank you. Okay. Concepts of molecular geometry. Of molecular geometry. And make sure to get your learning helmets because ow! Is it recording? So bam! Simple as that. Just divide 360 by the number of bonded atoms, right? Simple as that. So bam! Simple as that. Just divide the number of bond angles by the number of bonded atoms. Go. Bam! Bam! So bam! That's it. Just divide 360 by the number of. So bam! Press that button. Press that button, Billy. Get my shot, Billy. Alright. Peace out, guys.